All right, so we just have one more topic to cover in chapter five, and then we'll move into six. So in chapter five, last time we looked at the binomial distribution, and we also learned how to calculate moments for the binomial distribution as well as probabilities. But what we saved for last here is the Poisson distribution. And I did mention that although there's a third distribution in this chapter, the hypergeometric, we will not have time to cover it and will not be in any of your assignments or any exams. So I just want to quickly run to the Poisson distribution and then we can move on to six. So chapter five is where we introduce the concept of probability distributions and random variables. And we saw that there's two different types, discrete and continuous. So here in this chapter, we're looking at the discrete random variables and probability distributions. In chapter six, we'll move on to the continuous versions. Anyway, so everything we're doing here can be done algebraically or with our calculators. So we'll do both of them. And then later on, we'll do some Excel and we'll see how these probability distributions can be implemented in Excel. Anyway, so what is it that separates the Poisson distribution from the the binomial distribution? With the binomial distribution, what we're looking at is a situation where we have a repeated series of trials. Let's just summarize this real fast. Based on a series of repeated trials of an experiment, where trials are independent of each other on each trial of the experiment. There are only two possible outcomes, which we call success and failure. Now, which one is which depends on what you're trying to find. In the case we're looking at with the coin flipping experiment, we let heads be the success and tails be the failure, but it could have gone either way. All right, it doesn't make any real difference as long as you're consistent. And of course, we have a formula that lets us calculate binomial probabilities. And can certainly, and we did so, we did quite a few of these as a matter of fact. But then we also have moments. These are actually shortcut formulas. And so we're happy to have these formulas because they are quite a bit quicker than the general formulas that we did a while ago. Let's see. It doesn't want to let me copy it. Hold on a second. Yeah, sometimes it can be slow. Sometimes it doesn't work at all. All right, let's try that again. Yeah, it's having a rough night. I don't know what causes that. It's just it's a good product. It's just that sometimes it just doesn't work. No, all right. It's clearly it's probably better. I'll just do this myself. Um, yeah. Oh, wait. It actually woke up. Hold on one second. All right. Anyway, the point of what we're seeing. Oh, okay. I should have known. Anyway, the point of this part is that we started out by introducing the formulas that apply for all discrete random variables. Okay, if you remember, they look like this. So for the expected value under normal conditions, what you have to do is go through all the different possible values of x and multiply by the corresponding probabilities. And then for variance, what you have to do is take all the x's, subtract expected value, square it, and multiply by the probability. And then for the standard deviation, you're just taking the square root of the variance. So the ones on the right always work, no matter what discrete random variable we're looking at. They always work. The problem is they can be very time consuming. The ones on the left, these are the shortcut formulas that are only used with the binomial distribution. So it's very helpful to know these. It does speed things up a bit. And for pretty much for any of these distributions that we'll be looking at, there often are formulas that we can use, shortcut formulas, instead of the general versions of these moments for discrete random variables. Okay, so now this is the binomial distribution. We know how this works. We did plenty of examples. We know how to calculate binomial probabilities. We also know how to calculate these moments. So what about the Poisson distribution? What makes it different than the binomial distribution? Well, basically, this is used to represent one of two things. First, it can be used to represent can be used to represent the number of events that occur per unit of time, or to the number of events that occur per unit of distance. Okay, now pretty much all the examples we'll be looking at involve time somehow, but like let me just give you a quick couple of examples of this. So for the first one, Poisson distribution would be used to determine the probability that a given number of, let's say, cars pass through an intersection in the next hour. Okay, so you see here, we don't actually have trials going on. Instead, we have time. Time elapses, we observe the number of cars. The distribution of the number of cars is following the Poisson distribution then. So we also, for example, could say it could be used to determine probability of a given number of, let's say, defects per yard of cloth. Okay, so we're manufacturing cloth and we're worried about defects. And so if we measure, let's say, a yard of cloth, we'd like to know the probability of getting a certain number of defects over that yard. But most of the time we'll be using time here. Okay, but it's good to know that there's two ways this could be used. In fact, I actually saw an interesting example of this in a book where they were using it to figure out the probability of getting a certain number of chocolate chips in a cookie, okay, where they're all assumed to be the same size. So we're like, well, the probability that this one cookie that we pick at random has at least 4 chocolate chips in it, that actually could be described with the Poisson distribution. All right, anyway, so what we have to do here is show the probability formula that we'll be using to calculate Poisson probabilities. And where is it? Oh, that's the wrong chapter. Hold on. Here we go. Now you can see it looks a little bit simpler than the binomial formula, and it is. So first, let's figure out what these terms mean. So mu is the mean. Think of it as, if we're looking at time, this would be the mean number of events per unit of time. If it's distance, it would be the mean number of events per unit of distance. Okay. Then we have E. E is a constant. It's approximately equal to 2.71828. And X is the number of events that we're trying to measure. Okay, so let's just say that let's make up a quick example. Let's use the chocolate chip example. That might be fun. Suppose that we know from experience that let's say, a chocolate chip cookie with a 1 inch diameter has three chocolate chips. Okay. Now, of course, we know that, when you make a batch of chocolate chips, I mean, the cookie dough, the chips distribute themselves. You mix it up, and sometimes a cookie has a lot of chips, sometimes it doesn't. Um, it's completely at random, as long as you stir it up properly. So, what we're going to do here is ask, what is the probability that a cookie only has one chocolate chip? All right, now that let's just say that for some reason that would be if let's say you are the baker that's producing these cookies and you've decided that if any of the cookies doesn't have at least two, then you'll well not throw them out, but maybe you'll eat them yourselves instead of trying to sell them. You'd never throw them out. That would be ridiculous, but you might not be able to sell them. So instead, you you might have to do the unthinkable and eat it yourself. So we want to know the probability of this happening. So um, the three is that mu in the formula. This is the known average. Okay, we know from experience that on average there should be three. So mu is three, but here we're trying to figure out the probability that there's only one, which means that x is the one. So we're going to have, all right, now three to the first power is just three. One factorial is just one, by the way. And then e to the minus three power is approximately, from your calculator, point oh four nine. Let's just round this to 0.0498. All right. So we ultimately end up with approximately 0.149 4. Okay, so that's the probability that a given cookie only has one chocolate chip in it. Or we could have something involving time. Suppose, for example, that let's see. Suppose that imagine that you're walking around in the city and there's a pizzeria that's so popular that at any given time, there's five people waiting to get in the door. Or actually, it's probably maybe not the best one. How about this? Um, suppose that, okay, how about this? Suppose you're in a pizzeria at, during any given hour, on average, a pizzeria produces, let's say, 10 pizzas. Okay, so you stand there for an hour, you watch the pizzas coming out of the oven. On average, there's 10 of them. What is the probability that during the next hour, there will be 9 pizzas? Okay, so here the key, the whole thing is that it's so many pizzas being produced per hour. So the mu is 10 because that's the average that we know from experience. Okay. On average, there should be 10, but not always. Sometimes it's more, sometimes it's less. So the formula is, again, is up here. Let's copy this down. Um, So remember, this is going to be 10. Actually, let's move this up here so we can see it better. Oh, it doesn't like that. There we go. All right. So mu is 10, 10 to the ninth, e to the minus 10 over 9 factorial. Now, these are really large numbers. So I'm going to multiply them all out and divide by 9 factorial. Oops, made a bit of a typo. Hold on one second. Okay, I've got 0.1251. Okay, so about 12.5%. All right, anyway, now you probably are wondering if there's a quicker way of doing this with the calculator's built-in functions, and the answer is yes. Just like with the binomial distribution, there is a formula in here that we can use. So let's go back and revisit the chocolate chip case. So remember with chocolate chips, U is 3 and X is 1. So how do we calculate this one on the calculator? Let's go over the second bars. Slow down. The one you want is called D. In my case, it's D, but it's spelled plus on PDF. Don't confuse that with the CDF. If you look directly beneath it, there's a CDF. When you're looking at individual probabilities, you're going to use PDF. So when you calculate or choose that one, it's going to ask you only for two things, mu and the X value. So you want 3 and 1. Okay. And then enter, of course, enter your choice actually. And it's going to come back with 0.1494. And this is just an approximation. It's like 0.491493 or something like that. But guess what? That's what we got here. Okay. And then with the pitas, we have mu 10, x is 9. So let's try this again with the 4. And this time the mu is 10. X is 9. So we type those in and let's see what we get. Uh, 10 and 9. And it's going to be 0.1251. Yes, exactly. Okay, so now you know how to calculate Poisson probabilities, and you know how to calculate it with algebra and with the calculator. All right, now there is one thing we have to keep an eye on though, and we'll see this when we get to the Excel. Um, Unlike with a binomial distribution, where let's say there's 10 trials, that means X can only be 0 to 10. With something like this, in principle, there's no upper limit on X. So what that means then is that, when you create a probability distribution, you might find that it's adds up to something which is ever so slightly less than one because you might be missing some of the ones that are extremely unlikely to occur. So we'll discuss that later on. But this one is a little bit unusual because while, on average, this chocolate chip cookie should have three chips, in principle, I can have a probability for 10 or 50 or 30 or whatever. As unlikely as they are, they're still possibilities. And so their probabilities would be a string of zeros followed by a one. Whereas with the binomial, there's only so many and that's it. It's limited by the number of trials. Let's put it that way. So anyway, with that being said, um, now, here's their example, arrivals at the emergency room. The number of patients on average arriving at the emergency room in a large hospital in a 15-minute interval is 10. So that means mu is 10. What's the probability of getting 5 arrivals in that same period on the weekday morning? Okay, so for this one, mu is 10. And X is 5. So we'll do this, just for the practice, we'll do it with the calculator and with the algebraic formula. 'This is supposed to be okay. All right. So yeah, the formula's up here. I had a typo in there for a second. All right, here we go. Oh God, I forgot the negative sign. Oops. Boy, that was a close call. Um, so all right, anyway, let's pop this into the calculator. 0.0378. All right, but let's just say that you'd rather use the calculator, which is fine. Let's see how that would work. All right, second vars, and then we scroll down to D. Okay, so that means it's going to ask you for mu, it's going to ask you for X. Then of course you'll hit enter twice. And when you do, oh, what do you know? It's 0.0378. All right, beautiful. Okay, now what about the moments? Before we forget about the moments, I mentioned earlier that pretty much all the different distributions you might run into will typically have their own set of shortcut formulas for calculating the moments. Sun is no exception. As a matter of fact, you'll probably be surprised by how simple these are. Yeah, it's hard to believe. That's it. the first two are the same, which is very unusual. The expected value of the variance are both mu, and then of course that means the standard deviation is the square root of mu. So for the chocolate chip case, where mu was 3, expected value, that means on average, how many chips should there be in there? And that would be 3, of course. What else could it be? The variance is also 3, though. And the standard deviation is the square root of 3, which is approximately 1.73. So all all Poisson moments are calculated this way. Okay, now it's time to do a little bit of Excel. Let's come back over here. And this is the spreadsheet that we actually started last time called Chapter 5 Examples. And we did this case. This one is it's a discrete distribution that doesn't have a particular name associated with it. We have here, this is the binomial. We did 2 different ways. We did the calculations directly, and then we used the cumulative probabilities. And then here we go. Oh, it looks like we already did number 4 is an extension of the binomial case. So we're going to do number 3 right now. And so here's what we're doing. We're calculating Poisson probabilities where mu is 10, okay? Actually, I should have labeled this a little better. That's better. Okay, so what's the formula for Poisson here? Equals Poisson dot dist, and the x is this number. The mean is, when they say mean in this context, they mean mu, which is D1 with dollar signs, of course, and then a 0 for cumulative. Cumulative, remember, the way that works is that cumulative equals 0 for individual probabilities, 1 for less than or equal to probabilities. Okay, and those are known as cumulative probabilities. So now the beauty of this is we can just drag it down. Now, here's the quirky part. I started to mention this earlier. If I sum these up, now I've cut off the number of x's at 20, but in principle, there's no maximum number of occurrences here. So if you add these up, you'll see that it doesn't quite reach 1 because we're missing x equals 21, 22, 23. They're very small numbers, but they're not zeros. So if you add these up, yeah, 9984. So there's still some missing, but unless you want to have like a list of hundreds of these, this will probably have to suffice. So, but you can see why this one doesn't exactly add up to 1. Now there's the graph. Looks nice, doesn't it? It kind of looks like the binomial up to a point. And then for the cumulatives, we can do equals Poisson dist. X is this number. The mean is the D1 with dollar signs. Cumulative now is 1. In this column, it's 1. Okay? Because we do want cumulative probabilities, and there they are. So, oh, we don't want this one. And you can see what it looks like. So the bars are getting taller because that is the less than or equal to or cumulative probability for each of these different values of x. Okay. So that's actually it for chapter 5. We introduced random variables, we introduced probability distributions, we introduced the specific cases of the binomial distribution and the Poisson. We learned how to calculate their probabilities with algebra and the calculator. We also learned how to calculate their moments. And then finally, we did it all in Excel. So now we're going to move on to chapter 6, where instead of having discrete random variables, they will instead be continuous, which means they have an infinite number of possibilities. And when that happens, you really do have to use the calculators. in Excel. You can't really realistically do it algebraically anymore unless you're a whiz with calculus. Okay, so let's see what chapter 6 is all about. So these are the three probability distributions that we'd like to work with um, in the chapter. They're all continuous. Hold on. Now, what's important to note here is that when you're illustrating a continuous distribution, you can't use a bar chart because we would need an infinite number of bars. Okay, now clearly that's not going to happen. All right, so what do we do instead? We have to visualize that there's an infinite number of bars, and we're going to connect the tops of those bars to create a curve of some kind. And so that's why they look like this. You've got the uniform, continuous uniform distribution, the normal, which is by a long shot the most important of all of the distributions. This is the one we use the most often, and then exponential. Each one has a formula, but we will not really be dealing with the formulas. We're not going to even attempt to do these algebraically. Instead, or at least, well, all right, maybe the first one, but for the most part, we're just going to use the calculator. So again, a continuous random variable can have an infinite number of possible values, which means it can take on any value within an interval in the real number line. Now, one of the consequences of this, by the way, which is very interesting, is that with continuous random variables, a continuous random variable can assume one of an infinite number of possible values. As a result, it can be illustrated with a curve instead of a series of bars. Okay. And in addition to that, one of the consequences of this is that the probability that a continuous random variable equals a specific number is defined to be equal to 0, which means we can only compute the probability of a range of values for a continuous random variable. So just as a quick example of this, let X be the time until the next phone call. Now, time can have a fractional component, doesn't have to be an integer, so that X is a continuous random variable. Okay, in other words, the time could be 3 minutes, 3.02 minutes, 3.1714 minutes. So the probability that the next phone call arrives, let's say, in precisely 2 minutes is equal to 0. But on the other hand, we can instead compute the probability. Let's say that the next phone call arrives between 1 minute 50 seconds from now and 2 minutes and 10 seconds from now. Okay, in other words, the probability that X equals 2 is not 2 to 0, but we can calculate something like this. Oh boy, a minute and 50 seconds is actually 1.8333 minutes. 210 would be, so in other words, something like that. So we have some probability. We don't know what it is, but it will equal a constant. We need more information to figure it out. But the bottom line is the first probability is just zero. The probability that it's precisely 2 minutes is zero. But the probability that it lands somewhere between 1 minute and 50 seconds and 2 minutes and 10 seconds is some specific constant, like zero point 0.3 or something like that. Okay. It's a constant. Of course, it's a probability. So it's bounded between 0 and 1, but we know that it's a number. It's not zero. Okay. So now these graphs represent the three distributions that we'd like to look at: uniform, normal, and exponential. So um, with a discrete random variable, bar chart used to describe it can be used to represent or illustrate probabilities. Using looking at the heights of the bars. So let's say just quickly make up a quick probability distribution. It could be anything. So let's say we illustrate this with a bar chart. I'll put it over here. So the vertical axis is f of x, the probabilities, and x is here. So if I wanted to know, for example, the probability that x is less than or equal to 1, I'd be adding these two together, and I end up with 0.50. But with a continuous random variable, it's a little bit trickier. Let's look at the uniform distribution here. All right, now what's interesting here is that the way this is defined, let's say here x has to be between 1 and 10. Every value in between is equally likely to occur because it's the uniform random variable. So if I wanted to know the probability that x is between, let's say, 2 and 4, what I'm actually doing is calculating this area, the shaded area under the curve. Now, one thing that we need to make sure of is that this rectangle has to have an area of 1. Because it represents probabilities, the area equals 1. And so if you notice, it is a rectangle, and the base is 9. Therefore, in order for the area to be 1, the base, actually, let me move this over a little bit. It's in the way. Oh, and so the base that we're looking for is the area between 2 and 4. For the whole thing, the base is 9, but we're after only that shaded region. So remember from your travels that the area of a rectangle is the base times the height. So this probability is the area of the shaded region. And the base is 2. 2, and the height is 1/9. So the probability is approximately 0.2222. Now, all continuous random variables will give you a probability when you calculate the area under a curve from the graph. Okay, they're all done the same way. So this is the uniform random variable, or think of this as the uniform distribution. And so the probabilities here are areas under a rectangle, which means we only have to calculate the base times the height, with the understanding that the entire rectangle must have an area of 1 because it represents probabilities. Okay, so in other words, we know that something in that rectangle must be true. Therefore, the entire probability is 1, which corresponds to an area of 1. So with these graphs that we're looking at, areas under the curve correspond to probabilities. Okay, they mean the same thing. All right. So you can see with the uniform distribution, if we're looking at the area between x1 and x2, it's going to be the base, which is the difference between those two, and the height, whatever that happens to be. Now, we can say the same thing about the normal and the exponential distributions, except for one problem. They are not rectangles. Therefore, the calculations of the heights will be very tricky. And that's where those formulas will come in handy, but we won't actually be using them. We're going to let our calculators do all the work because the formulas are very messy. Let's not kid ourselves. So the uniform distribution has one important detail that we need to know. The probabilities of x um, are all the same, or of x being, all right, let's rewrite that. Probabilities of x being in a given interval are the same for all intervals of the same width. Okay, so let's see an example of this. Here, actually, we can make a completely new example, I guess. Let's say here's a uniform random variable, and it's only defined between 1 and 4. Let's say make that 5. So the base of this rectangle is 5 minus 1, which is 4. And because the area of that rectangle has to be 1, that implies that the height is 1 over that 4. Right? Because again, the base times the height has to be 1. Now, if I want to know the probability that, say, x is between 2 and 3, the base is 1, the height is 1/4, it's a fourth. But what if I'm interested in the area between, let's say, let's try 4 and 5. It's the same. It has to be. So in other words, with the uniform distribution, it's the base that uniquely determines the probability. Any two rectangles with the same base, of course, have to have the same probability because they have to have the same height. So that's why it's called the uniform distribution, because all these probabilities are the same as long as they have the same base. But again, now these are easy. We don't need our calculator. And in fact, the calculator doesn't have this function. We don't need it. It's too easy. The rest of them, we do need help from the calculator. For example, let's take a look at what's next, the normal. Now, I did say the normal distribution is the most important in statistics. It really is. It's used everywhere. So, but you can see calculating probabilities from that curve will not be easy. Okay, because the function itself is very complicated. So how do we do this? Oh, by the way, here's the formal way of doing uniform probabilities. If you want to do the algebra, this is what it would look like. So I'll move this down a bit before we start to use it. So basically all it's telling us is that for any two endpoints A and B, the height of that rectangle will be 1 over B minus A so that their area is 1. And so I can calculate any probability in between by simply looking at the area of the rectangle that is created. Outside of the rectangle, the probability is 0. So the probability that B, for example, X is greater than B is 0 or less than A is also 0. It only has area in between A and B. All right, so that's the formality. But this is what you're actually doing. By the way, this distribution has its own moments. Um, they're squared. Okay, so those are the moments. And, again, you can see they're not terribly complicated. Oops. Okay, now we move on to the normal distribution. Oh, here's a good example. Let's just quickly run through this one. They're telling us that this flight of an airplane traveling from New York to Chicago or Chicago to New York is uniformly distributed between 120 and 140 minutes, which means that all of those times are equally likely. Okay, so you can tell from this definition. Now that implies, by the way, because the base of this is 20, this height is 1 over 20, so that the area is 1. And the formal definition is this. Okay, so the probability that the next flight will be between 120 and 130 minutes. All right, so look how simple this is. Base times height is 130 minus 120 times the height of 1 over 20. So there's a 50% chance that the flight will arrive between 120 and 130 minutes. The expected value or average time to the flight gets here. Oh, by the way, this is A and this is B. The variance all right, is 400 over 12, or 33.33. 33.33. And then the standard deviation is just the square root of that. Which is approximately 5.77. All right, so this is a classic example of the uniform distribution. By the way, there is a special case that we need to know about. That's often the case with these distributions. Special case, the so-called standard uniform distribution is the one where A equals 0 and B equals 1. So in other words, it looks like this. And that means the height is 1. This actually, technically, it's a square. Okay, it's a rectangle, but it's a square because the base is 1 and the height is 1. If it's standard uniform. For all the others, we have to be told the endpoints A and B. Okay. Now, the normal distribution. This is the one that will get the most use out of. Now, look at that formula. It looks pretty terrifying, doesn't it? But it gives us a couple of important ideas here that we need to be very familiar with. And that's the idea that it's characterized by two important variables in there, which are mu and sigma. Okay. So the rest of these are constants, except for the x. That's the variable that is normally distributed. So now let me show you some graphs to help us understand. Now, first things first, the normal distribution looks like this. We call it a bell-shaped curve. And the shape and location of that curve depend on these two values, mu and sigma, in the following way. So let's say we have two of these normal distributions. Next to each other. They have the same standard deviation, but they have a different mean. So when they have the same standard deviation like that, they have the same shape. But they have two different locations. If, on the other hand, the means are the same, but the standard deviations are different, this is what we get. All right, that didn't turn out so well. Let me try that again. Well, what I'm trying to get at here is that they both are in this centered at, let's say, zero, but this one has it's very close to the center. It's very tall and very skinny. This one will have a very low mean, a standard deviation, let's say, one, and this one will be quite a bit higher. So in other words, the mean determines the location on the real number line, that is, um, of each distribution, but the standard deviation determines or shows how spread out the distributions are. A higher standard deviation means the curve is more spread out. Okay, so that's the key between the two. A higher standard deviation means more spread. In this case, they both happen to have the same mean, though. So this is why we say knowing the mean of the standard deviation is enough to uniquely characterize the normal distribution. So there are infinitely many normal distributions, each with its own unique values of the mean and standard deviation. Okay, and once again, there's a special case, the so-called standard distribution is the one where the mean is zero and the standard deviation. Okay, that's important. We'll see this all the time. It's a common thing. We're going to use it quite regularly. Now, here's the question. Oh, by the way, the one thing we also notice here is that no matter what the mean and standard deviation are, the normal curve, as it's called, is symmetrical about it, regardless of the values of the mean and standard deviation. Okay, or you can think of this as the skewness measure equals zero. Okay. Well, not these are not perfect drawings, but hopefully you can see that they are symmetrical about the mean. And yes, here's the mean in the center. The standard deviation tells us how stretched out it is. The mean is also the highest point on this curve, and the median in the mode. So remember, if a data set, or in this case, random variable, is symmetrical, the mean and the the median and the mode are all equal to each other. That's one of the interesting features of a symmetrical distribution. The three are right smack in the middle. So yes, here they're showing you that these are the curves that have the same standard deviation because the shapes are the same, but the means are different. And oh, one more thing I do want to mention here that it may not be obvious from these curves, but they do go out forever. In other words, there's no maximum or minimum values. So they go from negative to positive infinity and everything in between. In spite of this, the total area under this curve is 1. Now, you wouldn't think that was possible given that it stretches all the way out to positive and negative infinity, but yet that's exactly what happens because this curve is used to represent probabilities. So areas under this curve can also be thought of as probabilities. So areas under this curve correspond to probabilities, just like the uniform. You can write that here, just like the uniform distribution. The difference being that the areas are easier to calculate with the uniform than the normal. Okay, this is going to be tough. That's why we do need the calculators. And yes, and here they're showing you, and these are much nicer curves than I could draw. Um, let's copy these into the notes so you can see them better. So the tall one has a very low standard deviation. The short one has a higher standard deviation, but they both have a mean of mu. Okay, whatever it is. Okay, that's at the center. Now, because the total area under these curves is 1, and because the curve is symmetrical, that implies that the area on either side of the mean must be 1/2. Okay, because it's the only way that they can add up to 1 and still be equal to each other. All right, anyway. Now, this is something they'll ask about in MindTap. I know they will. There's a so-called empirical rule, which means based on experience, where they're trying to show us that from experience, they know that for any normal random variable, and by the way, if you look at the axis, you'll see that here we have the mean. Now these two, if x is in between those two, that means we say that x is within, I'll just type this one, x is within 1 standard deviation of the mean, and the probability of this happening within 1 standard of the mean is approximately 68.3%. So in other words, they're looking at this area here. Okay, then you can do the with the same logic. We can do the same thing for being within 2 and 3 standard deviations of the mean. So this is within 2 standard deviations of the mean. Okay. And then for three, based on the same rule, that would be all of this. This is pretty much the whole curve, but not all of it. So what you're seeing here is being within three standard deviations of the mean. Probability, as you can see from is 99.7%. So as soon as I start asking you about the so-called empirical rule, this is what they're talking about. Okay. Now it's not, those are not the actual probabilities, by the way. These are close, but they're only approximations. We're going to see how to calculate the actual probabilities with our calculators and later on in Excel. Okay. Yes, in fact, chapter 6 has two different sets of examples. We'll get to those very soon. All right, now what comes next? Right, so they're introducing the standard normal distribution, which we already know. Okay, now by the way, this is an interesting side note. When, if you notice so far, every time we introduced a random variable of some kind, um, random variables are usually represented with X or by X. But in the case of the standard normal random variable, it's so important. It gets its own letter. It's represented by C. All right, so keep that in mind. Z. So we'll see why that matters in a bit. By the way, this formula, we don't really need it at this point in time very much. It was much more important in the days when we didn't actually have calculators to do all this stuff for us. Um, oh, what did I do here? I think I better move this. I didn't realize that was still down there. Okay, great. So in other words, we have calculators and we can calculate any probabilities we need, but when calculators weren't around, we had to rely on something called tables. And so there's this whole slew of these tables that were available. But this conversion enables us to use the standard normal distribution to compute probabilities for any other normal random variable X. Okay. So in other words, no matter what X is, no matter what its mean, no matter what its standard deviation, even if there's no tables available, we could always use this conversion formula to convert it into the equivalent form under the normal standard normal curve. And that could be used then to calculate the probability that we're looking for. So we'll do some examples. It'll make perfect sense. Right now, just be aware that this is the conversion between X. X is a normal random variable with mean, mu, and standard deviation of sigma, where Z is a normal random variable with mean equals 0 and standard deviation equal to 1. Okay, so that's how we go back and forth between them if we need to. Now, it's often not necessary when you have calculators, but it's still good to know how this works. All right. Now, they're, by the way, they're already giving us the Excel formulas. I guess they figure you want to get started in that right away. The function that we'll need for normal distributions, actually, there's two that we're going to look at. Norm.s.dist, and the inverse of that is norm.s.inv. So here's some probabilities that we'll be practicing with. Those are these, the two that I mentioned earlier. We haven't started these just yet. So let's see, where are we? All right. So ideally, we'd like to get a fair amount of practice with this because this is such an important distribution. And we can do it again with our calculators and with Excel. We're not going to use algebra for these. Once that's done, we're going to look at the third and final of our continuous distributions, which is the exponential, which is a little bit, it has a formula. All right, we can use a formula with that one. I don't think the calculators have this one, but I'm not positive. I'd have to double check. But for now, we want to focus our attention on the normal distribution. We want to get some practice calculating normal probabilities, because we're going to see this thing over and over again. In fact, if you look ahead to chapter 7 and 8, you'll see that it shows up in both of those chapters too. So there's one part of this course that we must not rush through, and this is it. So what I'd like to do, I think, given how late it is and how hot it is stop right here. And then the next session, we'll pick it up here. We'll do lots of examples of the normal distribution. And then in chapters 7 and 8, we can see some applications of this normal distribution. Okay, so I'll see you then.